Hey everybody, we are here. Wow, I gotta change the camera around again. How's everyone doing today? We can do some work on some 201. Let me just bring the contrast down. Does contrast need to change? I don't know. Every day I swear the camera changes, the lighting changes. Maybe I want to do that. I don't know. Maybe it looks better, maybe it looks worse. Who knows? Who's all here? If you're here, you get to ask the questions. You get to choose what we do for office hours today. I just look very purple. Maybe it's the shirt. But we've got Coca-Cola to wake us up. Let's do this. What shall we do? We might do some 201 here. Might do some, we'll see if anyone jumps in and has questions. Feel free to say hey in the chat if you're here. And let's go to Canvas and get some 201 pulled up because they have an assignment coming up here. We just did some of their work. And 320 or 474, if you're here, say hey. We'll see who all is here. We're getting 201 pulled up as we speak. And then we will do a little bit of correlation, which is funny because we'll be doing some 320 correlation soon too. So correlation might be the name of the game today. Correlation might be the name of the game. Oh man, there's a lot of correlation questions. So let me get the correlation over here on the screen. And let's see if anyone comes in here with questions. If you come in with questions, feel free to ask. We're just going to do some correlation in the background right now. And we'll do this. Let's get started here. Let's do some correlation. It's Wacky Wednesdays. Take us in there, Crash. You got it, man. Wacky Wednesdays. Or Throwback Thursdays. I don't know what day it is. It's Throwback Thursdays. So this question stumps a lot of people. It's kind of a good place to start. It's in yesterday's class video too, but a lot of people have to think about how are we reading this question? What does this data mean? The first thing you want to identify here is that this is a scatter plot. So with this being a scatter plot, you're looking at 2 seconds here. There we go. We're good to go. So with this being a scatter plot here, it's a bivariate relationship. And we have here the batch number, and we have here the number of broken pieces. And I think they're doing a point jitter because they have the points kind of off the axis. So when you look at this, we have here the batch number going up, and then we have here the number of broken pieces right here going across this way. And with this, you might see if there's a positive, somewhat linear trend to this. As batch number increases, then we see that number of broken pieces also slightly increases too. And you have to realize that this is 2 variables, not 1. That's the key to this question, is that this is a bivariate display because it's a scatter plot, and we understand that right here. Now down here you have a histogram or histograms to pick from. That might be the right answer. So when you look at this right here, the number of broken pieces is a univariate display. So we have here a bivariate display scatter plot, quantitative, and here we have a histogram, or which histogram is the right answer, and this is a univariate display. It's one quantitative variable. And what are they displaying here? They're displaying the number of broken pieces. And although there are 2 axes right here, it's still just number of broken pieces. So when you look at one of these, like let's take this, which one's gonna be the right answer? I think this one's the right answer. I've done this question a lot. So when you look at this one right here, you have to think about this. Here we have 0 broken pieces, and this is how many times it occurs. Here we have 1 broken piece, and this is how many times it occurs. Just to kind of show what this data looks like, let's kind of recreate this. If we were to recreate this histogram, we would need to write the data, and let's just show what the data looks like. Hitting the wrong button there. So here's what the data would look like. If you notice right here where there's 0, that would mean we have 1 observation at 0. We have 2 observations at 1. We have 2 observations at 2. We have 3 observations at 3. And I'm doing it by the height of the bar. 1, 2, 3. We have 5 observations at 4. There we go. And we have 5, 6, 7, because that's 1, 2, 3, 4, 5, 6, 7, 8. Is that correct? That's 8. 8 observations at 5. So 1, 2, 3, 4, 5, 6, 7, 8. And then at 6, we have 1, 2, 3 observations. Now we should get something pretty similar the way Jump plots it out right here. But this is what the number of broken pieces looks like if we do the histogram right here. And we should see a very similar plot to this. And here it is right here. There is our plot via Jump, and you can actually see the data there. So it's important you kind of understand where this data is coming from and how we're creating it, and that this is just a univariate display. These histograms are just univariate, and this is the data that created it. Like I can identify that there are There's one batch with 0 broken pieces. There's 2 batches with 1 broken pieces. That's how I was identifying these numbers right here. And you might say, you're probably wondering, well, how in the world did you, identify this as the graphic right here, this graphic? Well, when you look at this scatter plot right here, we're only looking at the number of broken pieces. So I'm going to have to fly around the screen real quick right here. And if you look right here, with the number of broken pieces, which is this axis right here as I point to it, this axis, if you go left to right, how many batches have 0 broken pieces? There's 1 batch with 0 broken pieces, and I'm just going left to right. And then I'm counting the dots, there's 2 batches with 1 broken piece, and then there's 2 batches with 2 broken pieces. With 3 broken pieces, there's 1, 2, 3 batches. With 4 broken pieces, there's 1, 2, 3, 4, 5 batches. With five broken pieces, there's 1, 2, 3, 4, 5, 6, 7, 8, and then 6 broken pieces occurred in 1, 2, 3 batches. So when you look at this right here, it's a little tricky. You have to realize that you're just analyzing the one variable in the histogram, and you have to be able to read it from left to right with how many dots there are on each one of these axes right here, because you're kind of collapsing it. I guess another way to look at it, this might help because I can see it visually in my mind, so I'm going to try to show it visually here. Let's do this real quick. And we'll hop right here. Watch this magic. Class is over. I've now got the class is over screen here I can use. Let me close. There we go. Okay, class over back. And we go here, and this might help visually create it also. I want to flip this then. Picture format. There should be a picture flip. And no, I want to flip that way. Good. Okay, hopefully this doesn't confuse everybody. But if you look at this right here and you were to drop these points down, we can show the jump picture on the side right here. If you were to drop these points down, like if these points were to like fall down, hopefully people can kind of imagining what I'm imagining. Like if this point fell down here, it would fall down into this bin right here. I wish I could do some transparency, opacity stuff. Can I do that? You know, we're gonna go for the all-star right here. I don't know if you can do opacities on these things. Oh, you can put in this graphic. We're gonna do the best possible way of explaining this question we've ever done. I wish, can we set an opacity on this? I don't know enough picture formats in Word. It probably doesn't have an opacity setting. Opacity is when you can like see through the image. But if you look at this right here, and I'll put it over here for the side. If you look at this right here, these 3 go down into this because it's just the univariate display. So these 8 dots would fall into this bin right here where 5 is at. If you notice, that's a 5 right there. And that's where the 8 dots go. These are where the 3 dots go. These are where the 5 dots go. And you can see 3, 2, 2, 1. And that makes the histogram. So hopefully that helps make a little more understanding how we're just really looking at the one axis. We're not looking at the batch number. That's the bivariate display. We're looking at the univariate display. Who all is here? Say hey if you want. We're just working a question right here. I'm just going to keep working homework quiz 6 and doing a few problems to help make sense of what correlation is, because that's a quantitative display of data. So this is the right answer, unless I picked the wrong one. And this is a very left skew. So there's a left skew here, right to the high, left to the low, whatever way the tail goes. It's left skew because the tail goes to the left. And what feature is prominent? What feature of the problem is more apparent in the histogram? The histogram shows the shape. I want to repeat this right here. Right here, this shows shape, center, spread, or that's what we would analyze with univariate quantitative data. With the bivariate, we are going to analyze strength, direction, form, and unusual features. Rewind the video and listen again, or listen now. In a univariate histogram, we analyze shape, which is like unimodal, right skew, gaps, outliers, that's shape. We analyze the center. If it's normal, we do the mean. If it's skewed, we use the median. We analyze the spread. If it's normal, we use the standard deviation. And if it's skewed, we use the IQR. When we do a scatter plot, we analyze the strength, which is going to be basically on a scale of -1 to 1 for linear correlations, with 1 and -1 being the strongest and 0 being the weakest. When we do strength, direction, and direction's positive, negative, or neither. So positive, negative, neither. And then when we do form, it's either linear or nonlinear, and that's kind of a gradient. Like this is mostly linear. It's kind of, it might be straight enough for QQ straight enough outliers. So form is either really linear or not linear. And then unusual features would be things like outliers. Like if there was a dot all the way down there, that would be an outlier. So which feature is more prominent in the histogram, the scatter plot? We're going to see the shape of it, so the skew, and what is more apparent in the scatter plot? The positive, somewhat linear, and I'm glad they say somewhat linear because that really highlights it. Check your answer. We got it. Look at that, 100 right there. Who all's here? If you're here, say, hey, we'll do a few more of these. This is where people are going to get tripped up on these questions right here. If you notice, we have some scatter plots. And when you look at scatter plots, you need to analyze the strength, direction, form, and unusual features of the scatter plot. So what we're doing with correlation right here is it's measuring the linear strength. So you can have correlations like this. And I think everyone will get tricked on this one, because if you were to draw around this, and I'll show you what I'm talking about. If you were to draw around this, what shape would it create? If we were to go here and we were to draw around it, what in the world shape would this create? We are live, right? How many people are watching? What should the chat actually be going? Because sometimes the chat doesn't connect via that. 2 viewers. Woo! So if you look at this right here, you can tell the correlation right here. The correlation is going to be very close to 0. And with a correlation very close to 0, we look for the one that's closest to 0, and we see 0.006. And so we got it. That one's 0.006. The easiest one to do next is to do this one right here, answer C. With answer C, if you take a look at it, it looks most like a -1. So we'll go here to our little drawing, and we'll delete everything, even Rainbow Pen. Sorry, Rainbow Pen. So we'll go here and bring up, no, go bigger. There we go. With this right here, we're going to draw around it again, and if you look, it looks like a -1. So with it looking like a -1, we'll go back to here. We'll look for the correlation that's closest to -1, and that's the closest to -1. And we've basically identified the extremes right here. Now we're just down to a positive correlation, which that's the only positive one. And we're down to the only -1 left. And we've done it, I think, unless we mistyped a number. Good, we didn't mistype any numbers. That's the always error that we're always going to make. Mistyping numbers all the time. This one right here goes over the QQ straight enough, no outliers. We will eventually say plot doesn't thicken, but correlation only has 3 conditions. QQ, which means both variables are quantitative. Is somebody's, or the, that says the hardness of water in terms of grains. Is that how we measure it? It's pH, water's pH, and its hardness measured in grains. Didn't know that's how we measured it. That is going to be quantitative. You notice it's a real number. And we have the pH, which is quantitative, so that means QQ. The next condition is straight enough. So back in the day, I got to give shout outs to Dr. Seaver right here. In Dr. Seaver's class, we would always draw on pictures. Sounds like a fun class, right? Sounds like you're back in elementary school, you get to draw on pictures. But now you have to do it with graphics. You have to somehow use statistics and draw on pictures. So if I were to identify that this is quantitative, that means that both the y and the x variable are quantitative. So we've identified that we can do correlation. This is kind of the first most important one, that if you don't have 2 quantitative variables, you're not doing correlation. If you have categorical, you're making mosaic plots. If you have quantitative categorical, you're making side-by-side box plots. And if you're doing categorical quantitative, you're doing logistic regression. So there's different things we do for different variable types. And that's why we teach you variable types at the beginning. So since this is quantitative, we get a scatter plot, and a scatter plot is a bivariate, 2 variables right there, relationship between quantitative variables. And this is the only time you get correlation. So when people say things like gender is correlated to height, gender is associated with height, gender is not correlated, because correlation is only for quantitative relationships, not for quantitative categorical or categorical. Those are associations. So it goes to say that correlation is a type of association only for bivariate quantitative. So correlation is a type of association only for bivariate quantitative. So we made condition 1. All that to say we made condition 1. Condition 2 is straight enough. So what do we mean by straight enough? We mean a straight line well approximates, No, I'm going to try to add in the red pen here. I've been wanting the red pen. So add another highlighter. No, add another pen. Really? If I click it and then I click here, why can't I add another pen? If I click here, it says add another highlighter. That's so weird. What if I want more pens? Because I do. I can only add another highlighter. Why can't I add more pens? Can I add another highlighter? Oh, is that the max highlighters? What? That is so crazy. It's like you get this many pens. Why? Why? It used to be that you could have as many pens as you wanted, I swear, but now. So we got to highlight this. We got to show what the actual form is, and look at that. It's with highlighter now. So that is the actual form right there. The actual form is very not linear. So something is either linear or not linear, and this is not linear. The last condition, QQ straight enough, it fails straight enough, is no outliers. No outliers would mean that we don't have extreme data points like down here. And we don't. So it passes no outliers. And the reason you check for no outliers is because outliers can drastically impact correlation. You can have values of correlation right here. Class is not over yet. Class is not over yet. 2 seconds. You can have values of correlation. Look, magic. We're over here now. So if we do core demo, let's do core demo right here. The reason you don't want outliers is because you could have like a correlation that's basically equal to 0. And if you look, this correlation here is extremely weak. And so we have this really weak correlation. It's like equal to basically 0. I want to get it exactly 0. No, I went way too high on that one. So if you look, we're getting a really weak correlation. I keep on making it go too extreme, but eventually we'll get 0. Eventually, it's trolling me. Okay, so I need to go up here. We are so close. There we go. It was worth it. We got a correlation of 0. And R is the value of correlation. But watch this. All of a sudden now we have a really strong correlation. So if you look at this, an outlier can drastically impact the value of correlation. It can make a weak correlation strong. It can also make a very strong correlation, like a correlation of 1, which is a perfect line. It could make that correlation very weak or negative. I actually made it negative that time. Now the correlation's weak. I'll try to make it 0. It's kind of a fun game. Can you figure out exactly where 0 is? We were so close a moment ago. So we're really close. The correlation, putting the dot right there next to my head, makes the correlation basically 0. And it was almost 1. It was near perfect 1. It actually showed it as 1, but I think there were some additional decimals we weren't seeing. But the correlation was really strong, and then this outlier makes it weak, basically non-existent. And you also saw right here, you can have a correlation that's positive, and then you could have an outlier like down here, and it makes it negative. So now the correlation here is negative. And you just have to think, if you were to put a line through this, where would the line go? And the line would now be negative, and here the line is positive. So you can see correlation can drastically change due to outliers. So what can an outlier do to a correlation? Anything. Outliers can do anything. That's like the biggest note you need right here. But this fails the straight enough. So these are 3 conditions you need to check. QQ, straight enough, no outliers. And wait. It's not linear. So good. Not linear. We can't do linear correlation. Here we go. Same sort of question right here. Let's go for the easiest ones first. You should... Oh, this one's way too similar. Darn, it gave us basically the same problem. There's other variants of this, but as you can see, this one's going to be the obvious one. So if we go for the obvious one, that is the strongest negative correlation. How do we know it's negative? Because the line goes downwards. I think everyone got burnt out on assignments. 3 viewers, say hey if you're in the chat. Who all's here? Mewbot's here. I think Mewbot's awake. Mewbot, are you awake? Are you like one of the people in the chat, Mewbot? When there was 2 people, it was just me and Mewbot hanging out. Thank you, Mewbot. You're always here. Maybe I'm not broadcasting online. I'll find out later. I'll go look at the VOD. Now, this one, hey, what's up, Guzzy? Feel free to ask a question. I'm giving you your 1,000 for the week for just being here. Why not? You get 1,500. You're the only one here. Ask a question if you have it, and I'll continue to work through the correlation. I figured I'd put this in a video for people to watch later and to maybe better understand these concepts and to get good grades on the MyPearson. So I was like, let's do it. Let's do, and feel free if you're like, hey, I'm working on this, we can work on that. So look at this. Do you see this one right here? This one we did earlier. We were showing that this basically has no correlation at all. If you look at this right here, we'll go and we will draw around it. And what do we mean by no correlation? We mean no linear correlation. This is a trick question we sometimes put on the test. there is actually a pretty strong relationship here due to the lack of vertical scatter. It's pretty tight around the form. But if you look at it as a linear relationship, it's very weak, and you can test the linear by drawing around it, and you can see that there is basically no linear correlation here. There's some sort of parabolic form to it, but the linear correlation would be close to 0, which means we choose the correlation that's closest to 0 for this one, and answer B is going to be 0.006. Now we're left with a moderately weak negative, and that's the negative right here. And then we have a positive that's moderate strong. One too many sevens there. And there we go, we got it. Here we go with the same sort of questions right here. It's just making sure we understand correlation. First thing I'm going to look at right here is I'm going to find the weakest correlation. The weakest correlation is going to be the one, if I were to draw around it, looks most like a 0, and it's that one. So that's going to be the closest to 0. Now, someone might say, wait a minute, is that negative? A lot of students have said to me, wait, is it negative? It's so close to 0 that it's like, I can show you right here. I'll go over to the correlation solver. Let's restart this. If you notice right here, if we do the whole like blob of points thing and we just kind of make a crazy blob, you'll sometimes get values like this is apparently a tiny bit positive right now, and this is now a tiny bit negative. So this graphic behind me is it's basically a correlation of 0, and so this just constantly solves the correlation, and that was exactly 0. But if you notice, all these correlations that I'm creating right here are very, very weak, and it basically just looks like a blob of points. So, put another point there. Oh, I thought we were going to get 0. I was like, there we go, there's 0. But if you put one here, you'll get a little positive. If you put one here, you get a little negative. So this right here is the weakest non-relationship. But we should also note that while this has a correlation of 0, we could still get a correlation of 0 if we do this. If we do this pretty well and make a really good parabola here, there we go. Look at that, really good parabola. And I didn't get a perfect 0, so I didn't get the A. But the correlation is right next to 0 right now, because if you draw around this, you will get a 0. There's no real linear relationship here. If I were to make this exactly 0, it needs to go down a little bit. There we go. Exactly 0. It deals with leverage for 324.74. I'm working on the leverage on that. Leverage is around the mean of the x. Yay, advanced concepts. Helping me out solving for 0. So this has a correlation of 0 because correlation only measures the linear strength. So when we're trying to assess linear strength, we have to think what way does the line go? So we can look at something like this, and we could see that this is a moderate negative correlation right here. And you can see it, or moderate strong now. And you can make it weaker by bringing the points further outside. If you notice, if I go further outside, it gets weaker because the blob gets wider and eventually becomes more like a 0. So if we go out here, we'll basically get just like no correlation at all, I think. There we go. And yeah, now we're kind of playing with it till we get like exactly 0. Oh, right. Oh, no, it's... Oh, I'm negative right now. That's why. It was hard to see the negative sign right there. This is the most fun I have. But if you notice, I took one that was like a slightly weak negative correlation and I made it into no correlation at all. And so you can see this one is negative. It's moderately strong. So we only want to get the negative one that's moderately... Oh, it's pretty strong. Yeah, this is the only negative one. This one's a positive linear. And so we go right here. And it's the second strongest. This one's stronger because it's tighter. And this is mostly linear, I should say. It's mostly linear. So we go right here. And yeah, that's the strongest because it's the tightest and it fits best around the form. So we're good. That's got that. This one right here really tricks people. This one. Oof, this one. Let's bring up the notes right here. And let's show where people get tricked on this one. So you don't have to solve the equations. You don't have to solve the equations for correlation, but you should understand a key concept. A key concept about the equations is that correlation is unitless. Correlation is unitless. Correlation has no units to it because correlation is based on z-scores. So with this equation right here, this is the key to solving this problem. And it is in the notes too. It says somewhere in the notes, correlation is based on z-scores, that they're unitless. But this equation right here is what the answer is based on. So when you look at this problem right here, I want us to think about this. If everyone in the class gets a 50 on the test, that's not like, or the average is a 50, I should say. The average on the test is a 50. And then I say to everybody, good news, I'm going to give you 20 points and make the average a 70. I mean, 70 is not all, why not? 30 points, 30 points. Everyone gets 30 points. Now the average is an 80. So if you scored a 50, what would your z-score be at start? If you scored a 50, you would have a z-score of 0 because you're the mean. Now, if I move the average up 30 points, you scored an 80, but what would be your z-score then? Because now the average is 80. Hopefully, if this was class, I'd get a bunch of answers here, I know. But think about it. I'll repeat the problem again because that's the answer to this question. If the average on the test is a 50 and you scored a 50, your z-score, because you scored the average, would be a 0 because, but Gussie, great job here. So think about it. If 80 is the new average, what is your z-score with an average of 80? If 80 is the new average and you scored an 80 now, what is your z-score now? Bingo. So check this out. What did not change about this? The z-scores did not change, right? So do you think correlation will change at all? Since the z-scores stay the same, like if I shift the distribution, will anything change about the z-scores? Exactly. So we just answered the question. This would not change, and the magnitude of the correlation would not change because the z-scores on which it's based would not change. The question is the exact same thing to what I was saying, except it talks about like adding something to a hurricane. It's like they're going to add 120 miles and they're going to do that for every observation, or 120 miles to each how far the predicted track would be. So they're shifting the distribution, but everything still has the same distances. So all the z-scores would stay the same. So all the mathematics we're doing would stay the same. So since the z-scores do not change, the correlation does not change. So the sign would stay the same, the magnitude would stay the same. And yeah, hopefully that makes sense right here, because z-scores are based on how far something is away from the mean. And basically, if you take a distribution and you just shift it over, everything stays the same distance from the mean. Like imagine my head is the mean, and here's like the highest and lowest, and I just move the distribution like this. Everything still has the same distance from the mean, and the z-scores are not changing. I'm just adding and subtracting. It's like this. It's I think I've done enough examples on this one, but hopefully this makes sense. It's a conceptual thing. It's related to the formula right here, and understanding that we didn't change the z-score, so the correlation does not change. Hopefully that helps out with that one. We're going to get the whole thing done. We're going to do this here. Okay, what do we have here? A study examined the brain size from an MRI of the cross-section of 4 performances of IQ tests for college students. The scatter plot to the right shows the performance IQ scores versus the brain size. Describe the association between the brain size and IQ as seen in the scatter plot. I think I've gotten this one wrong before. Dun, dun, dun. Be like, we won't be sad. No sadness. We can do this, everyone. Let's wake up. Let's do this. Okay. If I were to say anything about this, you have to think, would a line go through this? A line, if it went through it, would go up a little bit. So let's cross off some ones here. Strong. No, it's not strong. There's a weak negative. Nope, doesn't go negative. There's a moderate weak negative. Nope. Here we go. Here's the only 2 I see. Oh man, this is gonna be tough. I know I've gotten this one wrong before. Well, good thing we're doing. Yeah, exactly. Colin, ask our problem, so I don't have to do this one. Let me read the 2 answers that are possible. There's only 2 possible answers. There is a very weak or possibly no association between the 2 variables. There is a moderately weak positive straight association. Okay, that's where I think they've lost me, because yeah, that's what I think it is. Okay. If there is anything, it's not going to be straight. It's going to be, there's some non-linearity to this, because if you notice here, we've kind of got almost like a cluster analysis. We don't do that. But we've got this group right here and this group right here. And if you notice, there'd be a flat line through here and there'd be a flat line through here. So it could eventually like jump. I don't see the linearity to it. So I don't see a linear relationship. If you were to, I'll show you visually what's convincing me that it's going to be the super weak, and then watch me get it wrong. What's convincing me that it's going to be the super weak is if we do our drawing, which we should always do our drawing. So let's do our drawing right here. Move the microphone a little bit closer. Question 5, you got it. Let's do it. We will do that right after this one right here. If we were to look at this and look at it like this and look at it like this one is basically flat and this one is basically flat. And if we were to draw through it, we might draw something like this right here. So I wish it gave me the data because then I could just run the data and find out all the values. But if we were to draw through it, there might be some non-linear relationship. So if there is anything, it's pretty weak. What do you say, my Pearson? What do you say? I've got both sound effects ready to go. So I'm saying there is a weak or possibly no association between the two variables. We got it. Of course we got it. They're not gonna trick us. A little tricky on that one, just with this like wording, and this one's so easy. We're gonna do it so quickly. All you have to memorize for this one is QQ, straighten up, no outliers. And we're looking at the model of cars right here. So we have model of cars A. Wait a minute, models of car B. If this is quantitative, which is QQ, then we cannot do this because let's see right here, it's not quantitative, and we got it. So since it's not quantitative, we can't do it. Let's take a look at Colin's question here. Let's go back to the future. Let's do this. Oops. There we go. Let's do this. Question 5. We got a lot of the assignment done today. How's your day going, Colin? How are you doing? It is Haslam Friday. Haslam Friday, because no classes on Friday. We do have the statistical knowledge challenge every week. Come check that out. I am loading up the assignment as we speak. And here it is. Let's see how Colin's doing. Really good. Chilling at work, knocking out homework. Awesome. Are you at a Haslam right now? Let's see. I'm getting everything loaded up. I miss walking around UT. It's so nice. Like I miss just like going around, walking around, seeing people. It's just, I mean, probably everyone else is probably like, I miss that too. Yeah, look, sadness. We need new sad music, I think. I'll have to get some new sad music so when we play it, people are like, oh, what sad music is that? Okay, so let's go down here and go to question number 5. And so just 1, 2, 3, 4, 5, 6, 7, 8, right, 9, right there. And with this, we are looking at, now what is question number? Question number 5 is right here, right? Are you talking about this one? Are you talking about this one specifically, Colin? Is this one you're talking about right here? I think you are because it might be some, okay, it's exercise 4. And I will make sure that this one, so this is page 72, exercise 6. 2 seconds. What did I button do? 2 seconds. We're not class not over right now. There we go. Got it open. And here we go. You need the GTA wasted. That'd be pretty good. That'd be pretty good. I'm trying to think. I haven't heard that GTA sound effect in so long. So I think we're on this one. Okay, we got it right here. We are curious whether there is an association between the size of the party and whether or not someone smokes. Party size range between 1 and 6. So in this case, it's appropriate to compare the average between groups when y only takes on a few different values. Using the average is typically the best way to go regardless of what the distribution looks like, unless it's really skewed. Run associate to perform a test of significance using the default number of permutations. Why is the test inconclusive? Now, be very careful here. So this is just a small update to this assignment. I do want to state this. When you run, so write your student replace blah, 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 and then I bet that's the seed. Oh, and yeah, we're doing a sample for randomness. So put in your ID here. I'm just going to run this one. Okay. So this creates a random sample right here, and here's the important part. So with this code right here, you'll notice that we've got the suppress warnings on it because sometimes you can get the warnings. All the code is you're building an associate function. Colin, do you know the format for the associate function? Do you know the format, very important format for the associate function? We'll use it all throughout this class. What is the format for the associate function? What is the format for the associate function? Who knows the format? 100 points right here. What is the format for the associate function? Any ideas? Maybe why something? Why tilde something? Well, the associate, you are correct. So we type associate, and we get this, and then inside of it, we do y tilde x comma data equals. So we do this format right here. So we need to know our y variable, and the y variable is going to be, what was it? We were trying to explain party size. So here's what I'm going to do is I'm going to go to attach ex2 tips, and that makes it so I can type right here party size. Is it size of party? Look at that, size of party. When you attach something, oh no worries. Actually, I did that for me too. It's associate equals y tilde x data smiley face. I love it, Colin. It turned like mine into like a thumbs up or something. I was like, wait, what? Attach makes it so we can type in things like smoker and it reaches them. So with attach, you can actually use the variables without putting the data frame. And I think we have everything right here good. And did this overwrite? Yeah, overwrite ex2 tips. Yep. Figure 2 large for margins. We'll rerun the code again. And figure 2 large? Was it because of the font size? There it goes. I didn't know font size controlled that much. Maybe it doesn't. I don't know. Okay. So because we're dealing with like integer data, we're going to use the mean. So the question specifically states to use the mean. So because the question says to use the mean, use the mean. I can't state that enough. Usually, and Colin was in the morning class here, so usually we take a look at the what's to figure out if we use the mean or the median. Only use the mean because the question said to use the mean. Because it's integer data, yes, 2 statisticians will get 10 answers on which one you should use, because this is one of those iffy types of situations. But what do we look at usually to figure out means or medians? The question says to use the mean, though, so I'm going to use the mean. What do we look at to figure out means or medians? Which one is appropriate to use? The goal is to figure out if the distributions are normal. And so if the goal is to figure out if the distributions are normal, then we will use the QQ plots to check for normality. And if you're in 201, you heard about this earlier. You heard about the normal probability plot. Normal probability plots are these. It's a plot to tell us if it's normal. And the straighter it is, the more normal it is. And you can see those are kind of straight, but they do have, there's a lot of integer data right here. There's a lot of 2-party people. This is restaurant data, so there's a lot of parties with 2 people. And it kind of goes outside of the boundaries for how many observations we would expect to only have 2 parties. And so there's a little too much data in that area. So is it normal? Nothing's normal. So with this right here, let's take a look. The answer is it's not really normal, but nothing's normal. So you sometimes get warnings, and I don't know if this one output warnings. So you can take your associate and put it inside of the suppress warnings. So all we're doing is taking and putting the code inside of R can't find the associate. What do you do if R can't find the associate? Colin, you got this, 100 points. Where is associate located? If R can't find associate, where is associate located? If R can't find associate, where is associate located? And did I actually get a result? Where is associate? We actually don't need it inside of the suppress warning, so I'm going to remove it. So associate is found in library reg class. And you can confirm this by typing associate, and it appears. So associate is inside a library reg class, so you have to have reg class running. So if it can't find a function, it's because the function just doesn't exist. And right now we have to run library reg class. Colin, good job, 100 points right there. You have to run library reg class, and then you can see right here, do you see where it says reg class right there? That tells you the package that has that function inside of it. So it's saying this is a reg class function, like it exists in the reg class. It's like I really want to buy some Sam's Club pizza. So you could go to Walmart and get Sam's Club pizza because Sam Walton. And so they own both Sam's Club and Walmart. And so if you really want to use the associate function, you have to go to reg class. You have to have reg class running to go and run the associate function. So hopefully that makes sense. Like if you don't have red class running, like right now I'm like, okay, I want to run the train function. So I can't because train is inside of caret. So you see when I type train, it does not appear. And so if I go here to library caret and I load library caret and then I type train, all of a sudden the train function appears, which is how we do models with the caret package. So the reason I'm able to do this now is because I loaded up the train function. There's other things like if I wanted to check the skewness of something, I don't get the skewness. So there's no skewness function until I do library E1071 and I run that, and then I type skewness, and now I can check the skewness because it's in this following package. And you might say, well, why don't all of these just load up? I've got lots of packages on here. So I've got all different tons of packages like Shiny, and if you look how long Shiny just takes to load, it takes a second is how long it takes to load, not even a second. Plotly? I thought Plotly took a while to load. It takes a while to download, I'll tell you that. Yeah. It just doesn't load all of them up, so it's not like you might have packages that would overlap with each other on what they do or the names of the functions, so R doesn't load up all your packages when you start. So that's what we got going on right there, and here's the code to give the results. But one thing we want to do probably is we want to set a seed. This is something it doesn't tell you to do, but something I mentioned in class today. If I set a seed right here and I set the seed to 12, every time I run this, what will stay the same every time I run this? Good. What will stay the same every time I run this? If I set the seed, it'll still be this, but I'll always get the same this. That's our favorite word. I'm ready to go on the button. Our favorite word in this class, it'll still be the same this, but it will be this. What am I controlling right now by setting a seed? What am I controlling by setting a seed? It's our favorite word. It's like the word of the day. By setting the seed, Brian has controlled the randomness. Randomness and the permutations. Because the permutations are created via randomness. That's exactly right. They're going, the permutations are being created via the randomness. And you can see them appear down here below me. And they actually take the longest to appear because it's doing random permutations. So by setting this seed, I get the same random permutations. If you look at this down here, you'll see it's slightly changed now, and you'll get a little bit different of a graphic. You see there's like a little bit of a spike there next where it's touching it. And now watch where it says averages. That'll go away, or it'll change. Yep, not touching it. And if I go back to here, I can get it to touch it again right there at that little mark where it touches it, because it's the same result. It's always going to do this every time because I'm getting the same random result by doing the seed. If I don't set a seed, it will just be kind of random. You see now it's like way different. So the results will be different for the permutations each time if I don't have a seed, but if I put a seed in, once again, the edge is just going to be right there touching it like it was before that little peak. So as you can see right here, the seed allows you to replicate results. So let's review what this output is. You should always know all your output. So this will be like review of this output right here. Let's start at the very top. Up here, you have side-by-side box plots. Side-by-side box plots show you the what. You should know the general idea of what side-by-side box plots show you. It's going to be a categorical variable on the x-axis, which is like our yes, no on whether someone's a smoker. And then the y-axis is going to be quantitative. So you've got a categorical, quantitative, bivariate display. Run it in the bottom. Run it in the bottom. Try running it in the console, and that'll do it. So run it. I'll go over to where it's running. Try running the code down here. Just do this, run the code down here, and that'll ensure it pops up right back here behind you. Great question, Colin, right there. 100 points. Thank you for asking it. Always ask the questions when you have them in the chat. Even if you're here and you're like 201 right now watching this, if you have a question, ask, and then I'll work it. I'll work the question. Here we have histograms. Don't really, you're welcome, Colin. Don't really look at these histograms. Histograms are univariate quantitative displays. They're good, but whatever. So here we have a row of histograms for the no, which relates to this box plot. Here we have a histogram for the yes. And then this is the one that people always forget how to analyze. This one right here is a normal quantile plot or QQ plot for normality to check to see if the no group, because this is the no group, to check to see if the no group is normal. And we're kind of letting this one slide a little bit because it's integer data, not across a big vector. But I'd be iffy on this one. I've lost control of myself. There we go. I'd be iffy on this one because it does have a lot of departures from normality. The question says to let it slide, so I'm going to let it slide. This one right here also has departures because if it's outside of this area, it's more departures. And we do see that there's a right skew here, but always look at the QQ plots. So once again, these QQ plots for normality are related to the histogram we see, just so we can see the big example we were doing in class today. And if anyone's watching the video, which is a good way to review, if you were to take random exponential numbers, and we had 500 of them, so there's random exponential numbers, and if you were to put these random exponential numbers into a histogram, so let's take and make a histogram out of them, the random exponential numbers would look like that. And now if we make a QQ plot out of them, really, that's what it said earlier, and then I ran it again and it fixed it. I don't know why. I might have to reset it again. Like this morning it did the same thing. Okay, 2 seconds. I'm gonna save it. Watch this. You're gonna see some magic right here. I wonder, I don't know why. I'm reloading it right here. Okay. Watch this. You ready? I need to load up library reg class now. Maybe I had an overlapping, and then this morning it worked. I don't know why. I don't know why that fixes it, but it does. So if you look right here, we have a, I'm going to vanish for the moment. We have here a QQ plot that is very bent, i.e. not normal for a QQ plot, so it doesn't follow the red line, and the histogram is very right skew. We can repeat this process with data that's normal and see what we would get if it was normal. So this stands for 500 random normal numbers. It just generates 500 random normal numbers for us. And we're just going to store it into X, make a histogram. The histogram should look what? Unimodal and symmetric. It does. And then the QQ plot now for this is going to look very across the red line. And so it does. It doesn't look perfect. You'll get different ones that don't look perfect. And so you see some of them are going to have, well, that one's got departures at the end. So we should see a little bit of a skewness. Oh, looks pretty good there. So you can see here that these are normal plots and these are not normal plots right here. So these are the not normal ones, and these would be failures of normality, and we should use the median. So if you see a QQ plot that looks like this, it means your histograms generally look like this, but look at the QQ plot. This means use the median. If you see a QQ plot that looks like this, that follows the red line mostly follows the red line, that means your histograms probably look like this, which are unimodal symmetric, and you should use the mean. Once again, big review right here. Use the median because it's not normal, it's skewed. Use the mean because it's normal. Do not worry if there's a little bit going outside. If there's a little bit going outside the boundaries, that is not the end of the world. All of these are actually from normal data, so they all are good. So if you're like, oh no, there's a little bit outside, whatever, it's fine. Because if you look at the histogram, looks got a little bit of outliers right there, but it's fine. It's fine. Everything is fine. Where did I go? Here I am. I'm back. So we need to regenerate that output, which we had. And here's the output. So very important stuff on the QQ plot right there. Don't forget how to read a QQ plot. It's one of those things I just see people failing to remember how to do all the time. And down here at the very bottom, we have the random permutations. Now we're most concerned about this one right here. This is the random permutations. I'll go this way. Gotta go over here. It's hard to tell where I'm at. So this is the random permutations right here for averages. And here is the p-value right here. Cullen, does the p-value look very large or very small? If I'm circling the p-value right now. So right there is the p-value, right where I'm circling with my finger. So does the p-value look very large or very small for this problem? Because this is the p-value for the averages. Be careful. This red line is our F statistic. So this is the F statistic where the red line is at. It's at like 4.6. And then here I'll draw visually what the p-value would look like. The p-value visually is going to be the results that are as extreme or more extreme than our results happening by random chance, i.e. the permutations. So the p-value, we have a new highlighter. This is the p-value. The area underneath those bins right there. So the p-value right here looks very, 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 very small. And so when we go back to the output, we can see the p-value. I don't like the way the output looked. 2 seconds. I just want it to be all in like, here we go. We can see the p-value right here for the averages, which relates to this graphic here that we're just looking at. The p-value is very small. And remember when we said the discrepancy was like 4 point something? That's the F statistic right there, which tells us the variation between the groups was 4.5 times larger than we would have expected due to random chance. So it's a good bit of variation between the groups, between the averages between the groups. Last but not least, especially with our set seed, what do we notice here? That when we ask the question, is it statistically significant? We would say yes. But down here, are we confident it's statistically significant? Are you confident this is statistically significant, Colin? Are you confident this is statistically significant? Because it is statistically significant by way of estimated p-value, but are you confident that it's statistically significant? Are you confident that it's statistically significant? You're like, I don't know. Because you'd be saying, I think the p-value might be as low as this, or the p-value might be as high as this. Like if you look, this is the p-value estimated, and we think, maybe it's as low as this or as high as this. What do you think? Are you confident it's statistically significant? No, because it contains 0.05. And the big thing here is if this interval contains 0.05, great job there, Colin, 100 points. If it contains 0.05, that's a bad thing. We want the interval to be either completely below 0.05 or completely above 0.05. And why do we want it completely below or completely above? Because if this is completely below, and here I'll do a drawing right here to help, like we take, okay, let's take p-values go from 0. Oh, cool. It already put spacebar. It knows what I want. And p-values go from 0 to 1, and here's 0.05. So if your interval were to be the following, like if you had an interval here, interval A is completely below. So that means you'd be confident that it is statistically significant. Interval B contains 0.05. So with interval B, you'd be like, well, it might be statistically significant, or it might not be statistically significant. And interval A right here. But with interval C, let's go to interval C. Interval C, what would you say for interval C? For interval C, you would know it's what? So with interval C, you would say it's definitely this. You'd be confident it's what? Interval C goes from like 0.4 to 0.7. So with interval C, you would say it's definitely this. And these are kind of the three results you can get. With interval C, you would say it's definitely not something. And so hopefully this is some big help right here, because these are big concept review things that we're doing. So you really have the three scenarios right here of what could occur. Your interval could be completely below, which is scenario A, which means you're confident it is statistically significant. Your interval could contain 0.05, which means it might be statistically significant. It might not. Look how I have the two different colors of highlighter in there. And then with interval C, the interval is completely above 0.05, meaning you're saying, oh yeah, it's not statistically significant, we're confident. So notice that your p-value is going to be at like the center of it. That's your estimated p-value. But then you create an interval to estimate around it of what it might be. So you get the p-value here, and the p-value is at the center of the interval generally. It's a little skewed interval sometimes. But the p-value is towards the center of the interval, and then if the interval contains 0.05, you're saying, well, maybe it is statistically significant, maybe it's not. And we have a scenario like scenario B right here. Let's look at scenario B, which we basically have in our output, because we have 0.05 in the interval, and that's not a good thing. So what does it say? If 0.05 is in the range, change permutations to a larger number. And I think this is like 2,000. So we're going to do a new argument by hitting enter. And I do permutations equals 2,000, or do whatever the assignment says. I'm just kind of showing an example right now. And with a larger amount of permutations, the interval will get tighter. It doesn't go up or down. That's a trick question I write on the test sometimes. But the interval gets tighter because it's better estimating. So with more permutations, you get a better estimate of the truth. And whew, we just barely got below 0.05, as in we barely don't contain it. So if you look at this interval now, we still have a statistically significant p-value, meaning we are statistically significant, and we are now confident that we are statistically significant. Does this make sense here, Colin? How does it look on this problem right here? This was a really good review of this output. Everything works the same for the median. Right now, the median is statistically significant, but we are not confident. If you look at this output now, and we'd probably need a lot of permutations if that's right on 0.05. Oh wait, that's the mean ranks. Oh wow. Whoops. Here's the median. And the median's not statistically significant. The median has no difference. So think about this. There's no difference between the medians, so it's not statistically significant. I guess the last thing right here is to talk about the practical significance of this. If I'm going to gauge the practical significance of these numbers, I need to talk about the difference. And this is a huge thing people are going to get wrong on this assignment, is we need to take and subtract these numbers and talk about what is the actual difference between these numbers. So when you look at the difference between these numbers, you need to talk about it. We're talking about party size based on if someone is not a smoker or is a smoker. And right now, this difference is statistically significant, which means it could be practically significant. And it's basically, Colin, help us out here. When you think of this in terms of people, this means the non-smoker parties about, if you were to tell your boss, you'd say, well, a non-smoker party about has this many people more on average. And we're talking on average. It's not like there's a literal this percent of a person. But if you were to talk about this in terms of money, what would you say right here? The non-smoker parties generally have about this much of a person more on average for all, if we do repeated trials of viewing non-smoker parties. What would you say if you're talking to a boss? You'd be like, well, the non-smoker parties generally have, you could, not 26%, but think about this. Like, this means that the non-smoker parties have 2.673 people on average. Like, if you go to a restaurant and you look at the non-smoker parties and you average up how many people are in the parties, non-smoker parties would have 2.673 people. And if you go to the smoker parties, they would have 2.409 people. So this means that the non-smoker parties have about how many more people, if you were to just talk about it like a really kind of nice round to the number, it is 0.264 more people, but I'd probably say about a this much more person. Like on average, there is about this many more people in a non-smoker party. I would, I'd quote the number, but then, so I'd say on average, there's about this many more people in a party, and I'd put the number in parentheses is the way I'd write it up. It's just easier to understand if someone just hears because we all know this word. As one, you might know it. Since it's 26%, I would just round it to a quarter. I'd say there's about a quarter more of a person. So like, if you think about it, if there's 4 parties of non-smokers, you'd expect them to have one more person. Like for 4 parties of non-smokers versus 4 parties of smokers, the non-smoker parties after 4 parties would have had one more person in their party because they have a quarter more people on average, or 0.264 more people on average. So if you're a big business, and this is where the practical significance comes into play, if you're like a really big business, like let's say you're McDonald's or something, man, I remember when McDonald's has smoking. It's funny as you get old and things change about the world. I'll mention this later, but if you're a really big business, this could be practically significant. If you're a mom and pop store, it might not be. You also want to look at the way smoking and non-smoking impacts your other customers. But it just depends on the size of your business, and that's the biggest thing to illustrate here. And the practical significance would be related to, is it worth it to try to, non-smokers is generally are larger groups of people by a quarter of a person, but is that really a big amount to us? And that's for you to decide. But I was going to say, I was watching things. There's an interview. You should check this out if anyone's still here and listening to me. There's an interview. It was a TV show called I've Got a Secret. And I think the TV show was in the 1950s or 60s. And they had on a guy who was 5 years old. And oh, Colin, that's awesome. You should check this out. It's there was a guy on TV, I think in 1960 or so, and his secret was he saw Abraham Lincoln get shot. That was his secret. This is like in the 60s. This is when my parents are alive. My parents are kids. My parents are little babies, or they're 10 years old at this point. And this guy's on a TV show. Like they could have turned on the TV and saw this guy be like, he was super old. He was like 96, 97. And he's like, I saw Abraham Lincoln get shot. And you're like, what? You saw Abraham Lincoln get shot? You saw that. Because he was like basically 100 years old, and Abraham Lincoln got shot by John Wilkes Booth in 1865. So he was like the last living person to like be at the theater. So pretty crazy right there. And he was on TV. So pretty crazy to think that what he saw, to think he saw so many changes over the US, like he was alive during the Civil War and stuff. And then to think he's seeing TVs and he's seeing like, cars and stuff, I mean, he literally saw all the cars, and, he he really didn't get to see computers and stuff like that if he passed away in like the 1960s or 70s. He was really old on that TV show. He was pretty old. Not like a spry 96. He was, anyways. Watch him still be alive today. He's like 150, and that'd be crazy. He's like, yeah, I saw it. It's pretty cool. It's pretty interesting. It's just kind of really crazy to think what some people get to experience across their life, and it's kind of cool. It's kind of cool to think by the time you reach that age, what you've seen. I guess I'm just trying to be happy with getting old, as we all do. We try to make peace with it. But that's got it, Colin, and everyone else. We did some really good today. We did some good review today. We did some Stat 201. I'll put the timestamps in the video for people to come back and check out later. And this was a really good review of what we covered this morning, and we'll be covering this in 320 this afternoon. So always remember, these office hours are here to kind of like re-go over topics, to explain stuff, and this basically solves the problem. And we basically reviewed a lot of lecture today. So I think that's got it. I'm going to go answer some emails, get ready for class, but I will see everybody later. So you're welcome, Colin. You know what? Let's end with everything's fine. Everything's fine, everyone. Talk to you later. Bye.